Good morning everyone. My name is Yahia Amoura. Today I'm going to present a conference paper with the title of Short Wind Speed Forecasting Model using Artificial Neural Network and Adaptive Neuro-Fuzzy Inference System for the International Conference on Sustainable Energies for Smart Cities. This work was made with the support of Professor Isabel Pereira and Professor José Lima. The presentation is divided as follows. We start by an introduction. We present the objectives of the work. We present the wind energy trends. We present the energy issues. Then we present the study data and analyze them. We present the ANN model and we explain them. We present the ANFIS model and we describe them. Finally, we conclude the study and propose guidelines for future work. Let's introduce the problematic. The massive increase in population had led to a massive increase in fossil fuel consumption. This massive increase represents a real danger for our planet. For that, policy aims at other alternatives. Among these alternatives, renewable energies are in the heat of the class. Wind turbine generation based on wind energy becomes a subject of profitable investment, especially in terms of longevity that can go till 20 years if it's well maintained, and high capacity of production compared to the other energy sources. But this wind energy or wind turbine production suffer from several obstacles, mainly the intermittent of supply, since they are based on wind generation that is of irregular character. However, this intermittence gives emergence to a problem of stability in the power generation system. Therefore, a forecasting model of the wind speed is essential for the optimal operation of power supply with an important share of wind energy conversion. To do that, we present in this work two supervised learning models for the prevision of wind velocity, one based on artificial neural network and the other one based on adaptive neuro-fuzzy inference system. The performances of the two models are compared by their mean square error between the predicted and the desired outputs. Intended from this work is to develop a wind speed forecasting model, use a two supervised learning model, the artificial neural network model and the ANFIS model, validate the result with real study data, presenting the best model for short-term prediction. Portugal is performing huge advancements in renewable energies production in recent years, as shown by the graph. Known by its large production from hydroelectric, Portugal is also performing an interesting advancements of production by wind turbines. Energy issues. Wind energy suffers from intermittency, as mentioned before, which is a disruption caused by irregularity from wind itself. The wind blows at various speeds, so it is challenged to predict the amount of energy that can be collected at a given time. This means we need a predictive model to perform a preventions for energy reserve in case that the wind dies down for longer length of times. Wind energy is one of the most energy efficient ways to produce electrical power from renewable energies in terms of capacities, as shown by the graph before. The wind farm requires continuous and sufficient wind speed for proper electricity production. A good prediction of wind speed will improve the reliability of the management system and thus have high performance, for example, of microgrid systems. The literature has shown several wind prediction models. Among these models, artificial intelligence based on neural network, the SVM, physiologic, and combined neural network with physiologic. For that matter, in this paper, the wind speed is predicted accurately by two models of the artificial neural network and one model from the ANFIS, used in multiple local meteorological measurements. The proposed artificial neural network model used the previously recorded wind speed and temperature together, weighted by weight, to predict the future value of wind speed. Let's speak about the study data. The study data were collected from the laboratory level of InstitutoPolitécnico of Bragança in the north. The collected data are measured for a period of 1 year from the 1st January of 2019 to 31 of December of 2019. To forecast the future value of wind speed, we had measured the wind speed each 5 minutes using a nanometer and temperature for also each 5 minutes using a thermocouple CAT type. The data of temperature and wind velocity are displayed in a recording system for each 5 minutes and for each hour as shown here. The proposed artificial neural network model used the previously recorded wind speed and temperature weighted by WIG to predict the future value of wind speed. The prediction is done in terms of each 5 minutes and in terms of each hour. The structure of the neural network is composed of 3 layers: an input layer, a hidden layer, and an output layer. Let's explain the two proposed artificial neural network models. For the first model, the neural network is initially trained while employing the initial weights. Following the backpropagation principle, for the error correction, the inputs including the wind speed and temperature are weighted by WIG via the Levenberg algorithm that was chosen for its fast convergence. Hence, the neural network weights are updated to achieve more consistent level of predictions. The activation function is used for the output layer neuron. This function is chosen as sigmoid. Then the output of the activation function will represent the predicted outputs. However, the performance of the prediction model will be measured using the mean square error. Therefore, the feed-forward network with the backpropagation principle ensures the adjustment of weight, which is determined at the offline training as described here in the first flowcharts. So, for the second model, we need to know that in this work there are 1 million pairs of input samples. To achieve an accurate model, it is proposed to train the neural network with the most persistent value by eliminating the invalid samples. To do this, the latter are excluded from the dataset through a data filter. The filter returns a logical array whose elements are true when an outlier or invalid value is detected in the corresponding element of the dataset. An outlier is defined as a value that divides by more than 3 median absolute deviation. The adaptive learning process is described in the second flowchart. To evaluate the performance of the artificial neural network wind speed prediction model, it is proposed to test it with several configurations by changing the number of training, validation, and testing samples. 5 successive tests have been executed for each configuration. The results are evaluated by the best, worst, and average value of the resulting mean squared error. According to the computation results of tables 1 and 2, it is noticeable that the error value for an interval measurement of 16 minutes are less significant than the one of 5 minutes. The results can be justified by the large numbers of data sets involved in the training of the second model. The results provide more persistent or more pertinent mean square value in terms of precision by selecting training configuration composed of samples of 19% training, 5% testing, and 5% validated, adaptable to 5 successive tests considering both types of input data. As first conclusion, it is preferable to perform a prediction for each 5 minutes as short-term prediction for a best combination of training with 19% of the set of data, testing with 5%, and validate with 5%. In addition to adjusting the weights by the backpropagation algorithm for precision improvement, it is proposed to further reduce the mean squared error value by filtering out the most non-conforming training inputs by deleting the outlier value with a data filters. It is well shown that the results of prediction were improved by more than 15%. The second artificial intelligence model adopted in this study is the ANFIS model, framed by combining two intelligence systems, the fuzzy inference system and the neural network system. It has the potential to capture the benefits of both in single framework, Moreover, the adopted inference system is based on the Neuro-Fuzzy model, corresponding to a set of fuzzy of if-then rules that have the learning capability to approximate nonlinear function. The proposed model includes 5 layers, comprise 2 types of nodes, fixed and adaptable as illustrated in this picture. This model is tested for 5-minute sets data processed with a data filter. The linear algorithm had run through 1000 epochs, till the mean square error from the model has been successfully minimized to 0.11. The results of the ANFIS model have shown the effectiveness of this later compared with our artificial neural network explained before. To conclude, the previously recorded wind speed and temperature were used to forecast the future wind speed values in the horizon of 1 day with a time step of 5 minutes and 60 minutes respectively. For this purpose, 2 artificial intelligence models had been proposed. The first one was the artificial intelligence of the neural network based on the backpropagation algorithm, and the second one concerned the adaptive Neuro-Fuzzy inference system, SEGWINO-based. To improve the accuracy of computational results for both models, the input set of training data was filtered to achieve a set without outlier values. Several configurations were proposed for the model learning, and the best one, or the best configuration, was to opt for sampling of 19% training, 5% testing, and 5% validation. Comparing the mean square error for values resulting from the 2 models, the ANFIS has outperformed the artificial neural network model in terms of accuracy. As continuation of this work, it is envisaged to combine different learning mechanisms with optimization methods to obtain accurate results effective in short-term and especially long-term prediction that the 2 previous models could not deliver. Thank you for your attention.